So right now I just attended the previous lecture towards the end, and I saw it was on millimeter wave. And now we will be going into a little higher frequency. Millimeter wave is say up to 100 gigahertz. And now we'll be dealing with in terahertz communication. It is from 100 gigahertz to say 10 to the power 2 or 3 terahertz. So I will share the slides. So in you can say it is a sub-millimeter wave, because in millimeter wave the wavelength is of the order of millimeter, but here it is a fraction of millimeter, still less. So we'll see what are the advantages of using this terahertz and what are the applications. This is the outline of my talk. I will give an introduction to terahertz communication, then we'll see its features, the spectrum, then the challenges and benefits of terahertz communication, and we'll also see scope for current research. So terahertz transmission is a complementary wireless technology for communication networks. So in addition to the existing wireless technology, which is mostly in a gigahertz range, terahertz will be an additional transmission technology, and this will allow high-speed wireless extension to of the optical fibers beyond 5G. Now, in order to achieve high capacity, we need very high carrier frequency, because if the carrier frequency itself is in gigahertz range, we cannot have a bandwidth in gigahertz. So for that, we need a bandwidth of, we need a carrier frequency of terahertz, then we can have a bandwidth of gigahertz. So that is why for higher capacity, the carrier frequency should be increased to more than 100 gigahertz. Terahertz, as all of you know, it is a unit of frequency, and this is defined as 1 trillion cycles per second, or 10 to the power 10 cycles per second. So here, mostly the terahertz deals with frequencies between 100 gigahertz to 10 terahertz. This is the order of carrier frequency, and the wavelengths will lie between 3 millimeter to 30 micrometer. So terahertz lies between radio waves and infrared waves, and so it has some unique properties. Like radio waves can pass through the walls, concrete walls and buildings, but terahertz signals cannot pass through this concrete buildings, but it can pass through plastics and textiles, paper or cardboard. Unlike infrared, for infrared you need a line of sight. It cannot pass through these objects also. So terahertz will have some properties in between this. It can pass through some thin layers, but not very thick. And that has got some advantage also. If it doesn't pass through that, we'll see that. So terahertz transmitter is capable of transmitting digital data at a rate more than 100 Gbps by using 300 gigahertz band. So we can see that this is more than 10 times faster than 5G. In 5G, it is proposed to have 1 Gbps with mobility and up to 10 Gbps for pedestrian or for static users. So here they propose 100 Gbps data rate, which is quite high. And the bandwidth of terahertz frequency bands are obviously very broad, so they can be used even for indoor communication to transmit at terabits per second. For indoor communication, for outdoor it is 100 Gbps, whereas for indoor it can be in Tbps. So terahertz band enables wire equivalent wireless connection. That means you can get a very fast data rate, which is equivalent to wired connection. Then energy efficient micro and nano networks are possible. High rate links with moving objects. So even if the objects are moving, still a very high data rate link is possible, as shown in this figure. It can be connected to aeroplanes, it can be connected to drones or the static buildings, people who are moving. It's all this can be connected at a very high data rate at TBPS link. Now, what are the features of terahertz that make it so efficient? So let us see. It has a virtually unbounded capacity for supporting wide channels because the carrier frequency is in terahertz, so we can have very wide channels in gigahertz range, and so that is why extremely high data rate transmission is possible. But it requires line of sight propagation because, as we have seen, it cannot pass through thick walls like buildings or mountains. So in that case, if there is a line of sight propagation, it will be able to propagate at a high data rate. And terahertz devices normally operate in very narrow beams, which are close to optical wavelengths, and because they have limited capability to penetrate the materials. Then we have to integrate this with the existing wireless network. So there are many challenges in that. How to integrate terahertz with the gigahertz wireless networks. And for this, we require proper antenna siting, antenna placement, and also we need proper backhaul. The connection from the base stations to the different access points, all these requirements will be very stringent in this case. Then the current spectrum policies are limited to radio frequencies. So because so far only radio frequencies were used for wireless communication, so all the standards and policies are made for that only. Now it has to be extended for terahertz. Terahertz is also called greenfield frontier for spectrum policy. And why do we need this terahertz communication? This is because expectations are increasing. Day by day, we want to improve performance. Now, wireless communication, the applications are going to increase exponentially. They are increasing exponentially rather. And so the demands for high data rate is also increasing. And also we want higher quality of service. We don't want our signals to be dropped frequently. And we don't want to lose the connections frequently. And there should not be any latency. We want the data to be transmitted as fast as possible. So for all this, we need something more than the existing 5G. Not existing, 5G is also in its initial stage. But there are some limitations of 5G also. So we go for beyond 5G, which will be using terahertz. And some of such applications are virtual IoT, virtual reality, augmented reality, Internet of Things. So all this require very high data rate and very high quality of service. So 5G is supposed to cater some of these applications, like starting from smart homes to smart city applications, 5G is used. But whenever you see there are some limitations that can be addressed by beyond 5G techniques. So all this can be enabled by using, here we can see 5G usage. And some of this have already been obtained by using 5G, but some are still not in its initial stage. So we need 6G or beyond 5G to get all this. So we can see here massive machine type of communication is in smart home applications, smart city applications, voice also. Then we also have ultra reliable and low latency communication. This type of communication is required if you design a self-driving car. There you want a very reliable communication, because if the car is not getting proper signals, then there may be accidents. So this requires ultra level and low latency communication. Similarly, mission critical application, there may be many critical applications, maybe medical or space applications. They require very critical communication systems. And then also industry automation. Then other things are augmented reality, work and play, cloud. So all this require a very high data rate and reliable data rate. Now we'll see what is the spectrum occupied by terahertz communication. So this lies between microwave and infrared, as I told earlier. So towards the lower side, you see there is radio wave in megahertz, up to 100 megahertz, you get radio waves. Then we have microwaves in gigahertz range. And then in terahertz, specifically from 10 to the power 11 to 10 to the power 13 hertz is known as terahertz. Is used for terahertz communication. 10 to the power 12 is terahertz, but the frequency proposed for terahertz is 10 to the power 11 hertz to 10 to the power 13 hertz. And in this range, the bandwidth is 30 to 3 millimeter, 30 micrometer to 3 millimeter. And we can see it lies between microwave and infrared waves, which are both used for some applications. Microwave already we are using for wireless application, and infrared is also used for many applications. Here we can see as you increase the available spectrum, it increases the throughput and path loss also. And similarly, if you decrease this, then it increases the spatial coverage. Like if you go towards the gigahertz range, the coverage is more, interference is also more, and the use with mobility is also better. So with terahertz, the mobility, it doesn't support mobility much as gigahertz frequencies support. So that is why it cannot be used as a standalone. Normally terahertz will require the existing wireless communication microwave frequencies also. Here we can see what are the different frequency ranges for different applications. So you already, those who are in communication, they know this. Radio frequency range is from 3 kilohertz to 300 megahertz. And then we have microwave range from 300 megahertz to 30 gigahertz. Then millimeter wave from 30 gigahertz to 300 gigahertz. And then this is terahertz or sub-millimeter wave from 300 gigahertz to 3 terahertz. Then we have infrared from 300 gigahertz to 430 terahertz. And after that, you have visible light. So the proposed terahertz band lies between microwave and infrared, and it is about from 100 gigahertz to 10 of terahertz. So how does it increase the capacity? We know from Shannon's theorem, channel available bandwidth and is given by B log 2 1 plus SNR. So if you increase the bandwidth, of course the data rate will increase. But it is not that going on increasing the bandwidth will simply go on increasing the data rate. This is also restricted by signal to interference isolation. So there is an optimal value after which the cost of infrastructure and interference will also become very high. So we cannot go on increasing the capacity. But up to certain value, we can increase this capacity with the bandwidth. And presently, most of the wireless applications are assigned to channels of 1.4 to 22 megahertz spectrum. Now, if we want to have higher bandwidth, like of the order of 60 to 160 megahertz, then it will increase the cost and complexity in the hardware. With this existing spectrum, it is difficult to get such high bandwidth. So moving higher in frequency has some disadvantages, but it provides a higher bandwidth. The disadvantages are absorption losses are more, scattering losses and penetration losses are more. So they will reduce the range, communication range. That is why terahertz communication cannot be proposed for very long distance. But for short range communication, this losses can be compensated by transmitting at a higher power or by getting bigger continuous bandwidth. So there are many technical challenges. So first we see the challenges and then we'll see what are the advantages and benefits of this terahertz communication. So the most important is high path loss. It has a very high path loss. Then it has low penetration power. So it cannot penetrate through many surfaces. The transmit power is also low. And the antenna gains have to be improved. Then also outage will occur if there is blockage. If we have many obstacles, then there will be outage. So the high path loss is because in terahertz spectrum, it has a very high path loss. At this frequency, the signal gets absorbed easily. And so even if we get high bandwidth, but path loss will increase, and it is very sensitive to humidity and the distance. So if the humidity is more, the path loss will increase. Similarly, if the distance is more, then also the path loss will increase. So it is found that even for a 1 meter distance, the path loss in terahertz is of the order of 100 to 200 dB. Whereas if you see in microwave, this path loss is about 1 to 2 dB. Even for a distance of 1 kilometer, the path loss is much less. So this is one disadvantage. And as we move higher in the spectrum, path loss is not constant also. If you go for higher bandwidth, then path loss still increases, and maximum we can get more than 200 dB also. So that depends on the operating frequency, and so we have, if you want a better throughput, then we have to find methods to reduce this. Then another disadvantage is low penetration power. It cannot go through walls and other surfaces. So for mobile communication, this is a big challenge, because with gigahertz frequencies, it can easily go through walls and other surfaces, and so you can receive the signal inside a building easily. But with terahertz, if the signal has to go to inside the building, then we need the support of existing gigahertz communication. And otherwise it will reduce the coverage, and this is very sensitive to blockages. If there is some obstacle between transmitter and receiver link, in that case we will have a sudden decrease in the received signal power. So for better communication link, we require a perfect line of sight communication. And if you are going for non-line of sight communication, then that depends on the surface type. And it is mostly this communication is possible because of the second order reflections, because it cannot pass through the wall. So because of reflection only, the signal can be transmitted to inside the building or beyond some obstacle. Okay. And sometimes you may need some additional mirrors or lenses for transmission for non-line of sight. So to compensate for high path loss, the transmit power has to be increased. But it is difficult to get high transmit power also. for antennas operating at such high frequency. Because as we go higher in frequency, the transmit power reduces. And now transmitters use a transmit power of -5 dBm for 650 gigahertz, and for 800 gigahertz, the transmit power is 0 dBm. So we cannot increase the transmit power also to a very high value. So although 1 to 2 gigahertz channel, but if you try to use a very wide channel, in that case, we have to increase the. We need a very high power, so that is why it is not suitable for very long distance communication. Because if the transmit power is limited and path loss is more, the received signal power is going to be less. Then another method by which we can increase the received signal power is by improving the antenna gains. Because if the received SNR is above a threshold, then only the signal can be decoded. And the received power will be directly proportional to transmit power and antenna gains, and is inversely proportional to path loss. So as we move higher in frequency, the path loss is increasing, transmit power is decreasing. So we have only one option, that is to increase the antenna gain. And this antenna gain is inversely proportional to the antenna beam width. So we can use directional antennas with very narrow beams so that the antenna gain will be higher. And this is, we can see, significantly higher if we are using narrow antenna beams. It increases the antenna gain by 27 to 45 dBi. And this is quite high because in case of microwave, we are getting, even if we use an omnidirectional antenna, we get a gain of 1 dBi. So this is 27 to 45 times higher. So this will compensate for the decrease in received power due to low transmit power and high path loss. Then very low penetration power and narrow beam widths can result in frequent link failure, because this narrow beam width will be towards the receiver. Now if the receiver is moving, then he may go out of the width, and then there may be link failure. So this is also a problem. If you design very narrow beam widths, there may be frequent link failures, or sometimes outage may occur. Outage is normally due to blockages. So if there is some obstruction between transmitter and receiver, that will block the signal and outage will occur. Or it can also be due to change in device orientation. That means if the device is moving, and if it's even if its direction changes, because now we are using narrow beam. So if you move your hand also from one hand to another hand, then device orientation changes, and that also can cause an outage. Now to avoid this blockage-induced outage, that is because of the obstructions, non-line of sight communication is preferred, where the communication can be done through some reflected signals. So due to second order reflections it can occur. But mobility induced outages can occur due to orientation change. And so for this, the beam width, if it is very narrow, this will occur. So while designing, we should take care of these things. So mobility induced outage can occur due to change in the orientation of device, or if it is mounted on an object or kept on an object and that is changing, then also outage may occur. So to attain higher antenna gain, the antennas use narrow beam width. As we have seen, if the beam width is narrow, antenna gain will be high. But this requires perfect alignment between transmitter and receiver. And if we have a small scale mobility, like as I said, if you move your hands, that also results in misalignment, and so outage will happen. Okay, so we need mobility management to avoid this type of outages. Now we have seen so many challenges, but we'll see that the benefits are much more than the challenges. So that is why terahertz is being proposed. Now these are the benefits. Limitation of other bands. Other bands have got some limitations which are not there in terahertz. Then it provides a green field spectrum, higher bandwidth, frontal boost. We'll see each of this. Security, then interference friendly. Okay, green field spectrum is repeated here. Scalability and backhaul support. So we see what are the limitations of other bands. Terahertz band is adapted because one reason is we can get very wide bandwidth at this higher frequency, at this higher carrier frequency, and this will result in a very high throughput. Now, lower bands are used, less than 6 gigahertz, the microwave bands, and they are fully allocated and occupied. So it is difficult to allocate bandwidth for any new application and to get a very wide bandwidth out of that. And if you go for higher frequency like millimeter wave, they don't have enough free bandwidth compared to terahertz. So in millimeter wave, we have up to 100 of gigahertz band, and there also most of the frequency bands are occupied. And if you use infrared frequencies, they are susceptible to reflection, then noise, even from sun or any light. If light falls, then this infrared signals will get interfered. And similarly, power is also restricted for safety reasons, because if you transmit infrared bands with high power, it can cause damage to human eye. Whereas for terahertz band, this type of limitations are not there. It is not harmful for human body. So it can be used, even it can penetrate through skin also. So it can be used for some scanning purpose also, like X-ray. But X-ray is harmful to human body, whereas we can use terahertz for this, which is not harmful. So for scanning also it can be used. Other advantage is green field spectrum. So terahertz is said to be green field spectrum because it avoids the need to deal with the present users, the microwave users, and it provides an opportunity to implement new methods. So because here the spectrum is completely separate than the existing users. Existing spectrum allocation is completely different. So now you have a wide spectrum available, and so we can use any novel model for sharing or accessing that spectrum. And the ease of enforcement and innovation is there in Terahertz Communication. FCC has already invested in using terahertz. So already some research is going on in this terahertz band. And there is, of course, some restriction on spectrum use because some of terahertz spectrum is also occupied for some applications like satellite services, Earth exploration satellite services, then meteorological services, spectroscopy, which is used to study the what is there inside the atoms and molecules. But there are very few applications. So this spectrum should not be used, but still we have a wide spectrum available beyond this. So here critical primary users are this Earth exploration satellite services. So we have to avoid coexistence with this users in terahertz band. And if you avoid all this, we get only less than 10 gigahertz bandwidth. So that is there is a limitation on the spectrum. But it can be done easily as compared to microwave frequencies, because here almost whole of the spectrum is allocated and very few gaps are there which can be used for any new application. Whereas in terahertz, very few spectrum are allocated and most of them are available. So a terahertz interest group was established by IEEE. It is the standard is IEEE 802.15, and they are already doing research in this and trying to find applications for terahertz band between 275 to gigahertz to 3 terahertz. Then very high bandwidth is required in this case. So that is one of the attractive characteristics of terahertz. A very high bandwidth is available. We can get a large chunk of continuous spectrum as high as 250 gigahertz, which is not possible in lower bands. And so if you want to transmit at a very high data rate for some particular application, this can be available only in terahertz communication. And because of occasional path loss peaks, these bandwidth values are sensitive to humidity, distance, and operating frequency. So the path, you will get some path loss at such high frequency, and path loss will vary with the humidity, with distance, with operating frequency. So if the available bandwidth is from 50 to 250 gigahertz, we can use the bandwidth of 50 to 250 gigahertz with less path loss. If we go for very high bandwidth, then the path loss will increase. So we should have a system that can adaptively select the best spectrum range based on the environmental factors. Like if the humidity is more, then it can reduce the bandwidth or select the best spectrum where the path loss will be less. So we need an adaptive system for this. And similarly, based on distance also, if the bandwidth can be allocated bandwidth can be changed. So another advantage is frontal boost. That is, the terahertz can be integrated with the existing lower band deployment and work as auxiliary support. So in place of laying out all the connections, the existing lower band deployment can be used, like the connection from the base stations to all the access points can be used that are already there, and from access points to individual users can be given using this terahertz band. So by offloading high demanding users to terahertz, we can, and proper allocation of resources, the throughput can be increased. So it is not going to replace the existing microwave frequencies, but it is going to be used as an auxiliary support. So because there are many users who want very high data rate, so over a short distance, they can be allocated terahertz spectrum, and the data rate can be increased. So integration of terahertz with lower and mid band spectrum can satisfy high user demands, and they can also free up the spectrum in lower band for mobile users by sharing that spectrum, or by sharing the load. Some of the users can be allocated terahertz. So then other mobile users, because terahertz, as I said, is not very suitable for mobile users. If you are moving at a very high speed, then there will be path loss will be very high. So it is better to use it for either at lower speed or for static users. And then mobile users, if some of the load is given to terahertz spectrum, the mobile users will get more spectrum. Similarly, it can satisfy small user demands which cannot be satisfied due to lack of resources in the existing microwave range. Then it can also increase the coverage at the cell edge. So we can have some base stations at the cell edges, we can have some access points at the cell edges. Using terahertz frequency, they can increase the coverage. And high-speed upload and download can be done by using this terahertz frequencies. So these are some of the advantages. Then it is interference friendly. In lower band or mid band, like these frequencies which are being used for cellular application, most of them 2.1 gigahertz, 2.6, 2.4 and 5 gigahertz. Actually, these are used for most of the applications. And now due to terahertz low penetration, the interference to the inside the room will be less. So this is one advantage, because terahertz cannot penetrate inside the buildings. It will not interfere with the existing mobile users. And if it is used for indoor communication, then the interference will be contained inside the rooms and it will not go outside there or outside a cubicle. So after a few meters, you will not find any interference due to this terahertz communication, because the path loss is more. So after a few meters, the receive palm will be very small. So the interference reduces. So there is some advantage also because of this path loss and because of low penetration power. And we can use a spectral reuse is also possible because of this. As you know, we can do frequency reuse only because the signal level falls after certain distance. So that is why we are able to reuse the same set of frequencies in some cells which are slightly far away from the cell which is using the same set of frequencies. So here we can further reduce the distance and go for smaller cells because the interference will be reduced. So this is an advantage in a dense deployment of access points and user equipments. And as the number of users are increasing, so we have to go for dense deployment of access points. And if you use terahertz communication, then it will reduce the interference. And of course, there will be blockage because of walls or any other obstacle, but that will result in significant outage. And so this blockages also reduce the interference, but sometimes they also cause outage. Then another important advantage is security, because here we are using directional beams and limited propagation distance. So it can be used for secure wireless communication with the pencil beams, very narrow beams, and very highly directional antenna. The jamming will be reduced, eavesdropping will be less. If you are directional antenna, you are transmitting the signal in all the directions, so it can be intercepted by any jammer or any eavesdropper. But here, by using highly directional beams, that can be avoided. Then ultra high speed and limited communication distance can be used, and it can create secure links. Or it can be used like for unmanned aerial vehicles. There, if you want to control that vehicle, you can use a very directed beam, and it cannot be intercepted or jammed by other users. So this is very important. Then spreading the information across a broad bandwidth makes it difficult for an attacker to jam the system. So we can also spread the information and then transmit it. So scalability is also one of the advantage, because antenna size is directly proportional to wavelength, as we know. And when you go for terahertz frequencies, the antenna size becomes very small. It is in nanometer in size. So you can have very small antennas, and with the proper research, we can have dense deployment of terahertz. As you have read just now, you heard about massive MIMO, where we have a large number of antennas used at both transmitter and receiver. So with the further decrease in size, if the antenna size itself is in nanometer, it is easy to deploy them at the transmitter or receiver without interference. Okay? Because we want that the antenna should be placed so that it will form the channels between transmit antenna and receiver antenna, they should be independent. Then only we can get more degrees of freedom and we can use it for capacity improvement. So that can be done by using smaller antennas. And antenna will also be cheap. Deployment of this small antennas will be cheaper. Then with limited propagation distance and being interference friendly, terahertz is an ideal candidate for ultra dense network. Ultra dense network where we have a large number of users, large number of base stations, and large number of access points. So there, terahertz communication has a great advantage because because here the path loss is more, it will cause less interference to the other users. The propagation distance is also less. So this helps in easy and dense deployment of the devices. And it can also be used in body area network, nanobots, and Internet of Things. So this are used for medical applications, body area network and nanobots. Then similar to frontal support, we also need backhaul support. And one of the most significant assumption for using this terahertz is backhaul has a higher data rate compared to the frontal. So in the backhaul, we can use fiber optic cables, which use optical signals. But they may not support terahertz. But by using terahertz, we can have wireless communication. We don't have to lay this optical cables. So this will also reduce the cost and it will provide ultra high throughput. So upgrading fiber will be costly, but if you use that as a backhaul connection and then use terahertz along with that, it will be an advantage. So terahertz can be used as a baseband signal over fiber, and this requires less signal modulation. Or we can use terahertz as wireless backhaul. So if it is used as wireless backhaul, that is a great advantage because you don't have to lay the costly fiber optic cables. Then there are many other advantages, like some of the applications are high-speed on-chip communication, on-site video streaming, then spectroscopy, and replacing optical fiber cables in data centers. So for all this, terahertz can be used. It can also be used, as I said, to replace X-rays for detecting weapons. And it is harmless to humans in a controlled environment, and it doesn't contain any ionized radiation. Then it can also be used in some event. Suppose you want to monitor some event, so it is difficult to have human help, or to have a large number of police personnel for ensuring the safety of people. It can be done by using a swarm of drones. Nowadays, it is already being done. But for drones, if you use terahertz spectrum, it will be more advantageous. Because there you can get line of sight path also. And drones can be deployed at different positions. And they can send the information immediately, monitor the situation and send the information to its controls. Then also it can be used in smart home applications to monitor temperature, air quality, object movement inside the home, and send that information. So this is like a IoT application. It can be used in real time. So we see that there are many advantages of this terahertz communication. Even though there are many challenges, but the advantages are much more than the challenges. So there are many research issues. To overcome the challenges, we need this, and those who want to do research, they can do in these areas also. So one is we need test beds to perform more experimental evaluations and channel modeling for this. Already some test beds are there, and they are looking into channel modeling, channel coding, and field test. But most of these are constrained to below 300 gigahertz. So now we have to do research above on involving frequencies above 300 gigahertz. Then antenna design is also very important because we need advancement in antenna design, which will provide wider bandwidth gain and with perfect main load so that the interference will be reduced. And most of the current research assumes a perfect conical shape antenna beam, but actually in practical case it is not possible. So we have to try to get a perfect conical shape antenna beam. Then dynamic massive MIMO can also be used to overcome the high path losses, and they also may need cooperative communication among different devices. So antenna design and massive MIMO, dynamic massive MIMO is important. Then we have to design adaptive systems. We need some smart systems which can adaptively change parameters based on environmental settings, like the operating frequencies, the available bandwidths, or the achievable data rates. They are highly dependent on the environment. By using some machine learning or artificial intelligence tools, some optimal values for antenna parameters can be found, and then we can get the best of this terahertz band. Then access point specification is also important. To avoid high path loss, access points should be strategically placed in the indoor setting, and we can use terahertz plug. Their access points can be plugged to a data jack, like an Ethernet port can be used on a wall or part of another data device, and this can constrain the user mobility or coverage, but inside a room it can be used. And for a more mobile distribution, the access points may be broader. It can be distributed throughout the room to provide complete coverage. And due to low penetration power, terahertz cannot penetrate walls or objects. So this will reduce the coverage, but at the same time, and special coverage can be increased by using mirrors, or by using lenses. So then we have mobility management. So in the case of blockage, to continue communication, we have non-line of sight communication can be used, which will change the operating frequency band or wait till the blockage is removed. So these are some of the solutions: either use non-line of sight, or change the operating frequency band, or wait till blockage is removed. So mobility-induced outages can be maintained and avoided by proper analysis. Like if device is moving, so if a blockage comes in between transmitter and receiver, so we can either use a non-line of sight method or wait till the user goes out of that blockage. Beam alignment is also used sometimes, but it takes time. if there are multiple antennas, this may be complicated. Then as we move higher in terahertz spectrum, mobility management method becomes more complex. Then we can use terahertz spectrum to support mobile users by offloading some users into terahertz communication and freeing the spectrum in the lower bands. Rather than supporting the mobile communication, it will support the static users. Then some new access protocols need to be defined. Terahertz is sensitive to path loss and frequent outage scenario, as we have seen, especially if there are blockages or device mobility. The device is moving. So a single terahertz access point may have capability to cover multiple users, but terahertz may need multiple access points with seamless handoff and multi-hop communication. So we may need a multiple access points inside a room to have terahertz communication without any blockage. And for that, we need some changes in the algorithms of network. And it may also require support from lower and mid bands. If it is not able to provide coverage, then the frequencies may be shifted to the microwave frequencies. And this should be seamless. That means the call should not be dropped or the connection should not be lost during this offloading and making the changes in the connection. So this is important. Then the spectrum access. There needs to be a discussion among different regulators, operators, and manufacturers because it is important how the different frequency bands can be allocated to the user. Some of them will be licensed and some will be unlicensed. Like in present case, 2.4 gigahertz and 5 gigahertz are unlicensed frequencies, carrier frequencies, which can be used by any user. Whereas for specific applications like cellular application, licensed band is used. So here also, it has to be regulated. And terahertz can promote unlicensed use of a spectrum, like ISM band here also we can go. And also some amount of licensed spectrum will be required. Then there will be, of course, changes in hardware. When we use terahertz spectrum, then the data rate will be in terabits per second. And so the associated hardware has to be changed. We need to change the modulation, demodulation methods, and our filters, everything has to be at the required frequency. And since terahertz lies both in microwave and infrared, it starts from microwave and goes up to infrared frequency. So it shares the property of both wireless as well as optics. And so hardware should be able to process and convert signals between wireless and optics. Okay. So whatever hardware we design, they should be able to process both types of signals, starting from wireless to optical. And it needs to be equipped with beam steering techniques. So the hardware will be complex. And so if it is complex, normally the cost also increases. But again, care should be taken that it is not very costly, and otherwise it will not be successful. So some cheaper techniques should be used to reduce the cost. And some proposed technologies are silicon, germanium, and then CMOS technology, and gallium nitride, graphene. These are some of the technologies that are being proposed to reduce the cost, to get low-cost fabrication technology. Then safety standards are also very important. So most of the countries have restrictions on electromagnetic radiation because they say electromagnetic radiation is bad for human body. So there's a limit how much electromagnetic radiation is acceptable. Based on device transmit power and its application, there's a limit. Like in US, the FCC follows the standard for 3 kilohertz to 300 gigahertz. They have set some standards, but similar standards have to be set for the high frequency, for terahertz frequencies also. In the infrared band, also some limits are set for device operation. And terahertz is from microwave to infrared band. So this also will have some effect on the human body. It heats a surface that absorbs it, like human skin. If it absorbs the radiation, it will heat that body. And so we should take care of that. How much radiation should be there, that is important. To compensate for the high path loss, narrow pencil beams are required for terahertz communication. And this terahertz laser beams can have a thermal effect on human skin and tissues. So the safety standards have also to be considered. So then we come to our conclusion. The current challenges and benefits associated with terahertz spectrum we have discussed. And we see that there are many challenges which limit the deployment of terahertz for mobile applications. But there are many other characteristics which make it desirable for ultra-high speed communication. And this is a spectrum which can provide high bandwidth compared to traditional radio spectrum or millimeter wave spectrum also. But here the path loss is more. So it cannot be used for long distance and coverage is less. And then compared to high frequency spectrum like FSO, which is still high, terahertz is not very sensitive to opaque objects. And it passes through some objects, thin objects, and it also doesn't pose a risk for human eyes. So these are some advantages as compared to ultra frequency light. Then terahertz can provide high demanding applications and with 50 to 250 gigahertz of bandwidth. And if it can design proper methods to compensate for this high path loss, then we can have more applications for ultra high throughput. So its low penetration power makes it sensitive to blockage and mobility, but as I said, this is also an advantage for reducing the interference. So, but what is important is terahertz cannot independently cater to future demand. It always requires constant support from lower bands. This is because we have seen that there are some important challenges. It cannot be transmitted over long distance. And it cannot support mobile mobility. So for that, we'll have to use lower bands also. But along with lower bands, if you use terahertz, it can increase the capacity by a large amount. So to improve the deployment of terahertz in future high demanding services, we have to, the researchers, the manufacturers, operators all have to work regarding this, and then they should solve the research and policy related challenges. And already a lot of research is being done, as you can we'll see now. I won't put that slides, but a lot of research is being done in this environment, and most of the research is being done in jointly by University of Technology Finland, then New York State University, Georgia Institute of Technology, and there's a Waterford Institute in Ireland, then Intel Labs, and University of Finland. So they have done some research and found some measurements have been done. How much for indoor applications mostly they have done, and what is the path loss and how much is the received signal, and also they have used it for body area network applications. So this research is in early stage. There are many papers also published. So you can see these references. So these are the references. Thank you for hearing patiently. Now, if there are any questions, I will be happy to answer.
So, anyone have any question may raise their hand.
Thank you, ma'am. Ma'am, I'm Annapurna. Ma'am, I have only one question. Ma'am, can this terahertz communication be helpful for finite block length communication? Because in that case, if we are reducing the block length, ma'am, then how it will be implemented in the terahertz era?
Can you repeat it? Can it be used for?
Yes, ma'am. Ma'am, for finite block length communication, when we are using the block length is being reduced, like for URLLC type of services. So in that case, for terahertz communication, even the wavelength is very limited. So that's why how it can be implemented in terahertz era for finite block length communication, ma'am. Because we cannot apply that Shannon's capacity, ma'am. So maybe that was the concern, ma'am.
Actually, it is in very initial stage, so I don't think anyone has tried that. Always, if you think there will be some way to do it. Yeah. But, block length. So I think we have to discuss that, or we have to think about it, how it can be used. Because, as you said rightly, it is very high frequency, so the symbol duration will be very small.
Yes,
Still, I think it can be used. What would be the problem, do you think, if you go for terahertz? I think it can be used. There should not be much problem because your coherence time will be smaller. But in this case, the simple time is very small, so we can still combine a lot of them and use a block similar to what we are doing in microwave range.